Okay. Testing microphone. Mic test. Thanks. Ah, great. 5 people are here. Must be my students. And there's Crow. Okay. Hello, class. Good to see that you're all here, obviously. I do see 2 of you online on Discord, so these 2 people are here. And please remember that I have 45-minute classes, so which is essentially impossible. But okay, Crow, thanks for that opinion. All right, now we have 45-minute lectures, and today's week is 1 day shorter, so it's just what am I going to cover? Well, I'm going to try to cover 2 things this week. Okay, so the first thing is a sample consequence of Lagrange's theorem. So we're going to talk about, just to give you a sense of the power of Lagrange's theorem and how you can exploit it to great effect. We'll see one consequence, and then as a parallel story, I'll talk about Cayley's theorem, which is a purely sort of theoretical fact and kind of useless, like practically speaking, but very important when it comes to like situating yourself. If you have a bias towards groups that arise as physical symmetries of a set versus all the other weird abstract groups, that is a false distinction. And this is the content of Cayley's theorem. So it's more like a psychological thing. It's not, I've never seen Cayley's theorem actually used as a punchline in a serious proof, but it's good to know. All right, and the last part is always the concrete part, which you gain fluency with concrete groups that add more groups to your list of your big bag of groups, and we'll be talking about the alternating groups in that last 15-minute chunk. I'm sure it'll not be exactly 15 minutes, but okay. So let's begin with the sample consequence of Lagrange's theorem. So sample consequence. Okay. All right. So here's after the homework, especially the problem about groups of order 6, my class will truly appreciate how crazy this kind of a theorem must be to prove just by elementary, without knowing extra tools. How on earth you would go about this seems like a real pain. Okay, so here's an amazing theorem. So here's a theorem, and this is the theorem we're going to prove this week to illustrate the power of Lagrange's theorem. Okay, so here's the theorem. Let P be a prime number bigger than 2. Then any group of size of order 2 times p is isomorphic to z mod 2pz. So cyclic group of size 2p, it's either that or the dihedral group of the p-gon, the regular p-gon, the symmetries of a p-gon. So there's only 2. There are only 2 up to isomorphism groups of order 2p. Before this, the immediate consequence we had from Lagrange's theorem is that there's only one group of order p, where p is a prime, namely the cyclic group. Okay? So this is like a vast, we're doubling our sort of overall knowledge of how diverse can the collection of groups be if the order is a number of the form 2 times a prime. Kind of fascinating. And yeah, you should always think, how on earth was I gonna just prove this without the tricks that we learned? That's how you appreciate the tricks. Okay, so in order to prove this, the proof involves 2 ingredients. So I'm going to tell you the 2 ingredients. And everything I talk about this week is contained in chapters 6 and 7. So read those chapters, but we won't be able to cover everything in those 2 chapters. So if you read the whole chapter, you'll be ahead. Both of those chapters, you'll be ahead. Okay, so ingredients. The 2 ingredients are the following. I'm going to call them 2 things. So one is Lagrange's theorem. Okay, that's going to be the first ingredient. And the second ingredient is a good trick to know. Okay, we need to give a name to this trick. We're going to call it the h times k trick. Right? So the h times k trick is fundamentally a counting trick. This is a counting argument. And it's only useful in finite groups. All right? When you're dealing with finite groups, which we are, obviously. All right, so now what I'm going to start with is the HK trick. So here's the let's discuss this HK trick. You will love this trick because it gets you crazy information relatively cheaply. So the HK trick. Okay. It's not a trick, it's a tool, all right? And no one calls it the HK trick, but we're going to call it that. So here's the setting. The setting. You've got yourself a finite group. In fact, no. What you've got are 2 subgroups. 2 subgroups. And they're both finite. Of a group. Very important that they're both subgroups, not random subsets. Okay. Hollow Knight trick. That's interesting. Okay. So yeah, 2 subgroups finite of an ambient group G. That's your setting. And what you do is the content of the trick is as follows. Okay. So the question is this. It's a counting question. How many elements in G are of the form a little h times a little k, where h is in h and k is in k. In other words, here's the picture. Here's the picture. You have your ambient group G. Of course, it always has this identity element. And your two subgroups are kind of like this. Oh, maybe I do two different colors. A, H. Okay, now we're interested in all the elements in the group that are expressible as an H times a K. All right, so let's give a name to that set. So we're interested in this counting problem to the following. We're going to make a definition. We let H times K, like this, put the two groups next to each other. We let this equal the set of all elements, H times K, as H runs through all elements in one subgroup and K runs through all elements in the second subgroup. Now, in the beginning, for new people, new students, it's very tempting to think that H times K is again a subgroup. So it's very tempting, very tempting. That HK is again a subgroup. False. Here's the issue. Here's first, what I'm about to show you is not a proof. You have to go find, just go into one of your just a standard, go to dihedral group and you'll find a counterexample there. So you got to go find a counterexample to actually prove that this is false. But here's the fundamental reason why it's not so easy. All right, if you have an H times a K, H1 times a K1, and you multiply it by an H2 times a K2, you are not free to swap the order of the H2 and the K1. This is not, for instance, e.g., if you dream that maybe this is what works, this is not the following product. You see, you might dream that that would be the case. If it were the case, if H and Q commuted with each other, then H times K is a subgroup. So that's a extra little thing, and I'm basically giving you the proof of it. But the fundamental obstruction for H times K for the naive guess for why H times K might be a subgroup, why that's false, is because you can't just transfer this middle you can't swap this middle factor. You can't swap it. There seems to be no systematic reason why you can swap those, the order of those. So H times K is literally just all the elements you can obtain by taking a single product of an H times a K element. And so the question is, how big is this set? So this is the HK trick. How big is HK? i.e., what is the number of H times K? I'm going to use the symbol number in front of a set to denote like the size of this of a set. Okay, and I'll use the absolute values in the context when we have a group. That's the order. HK is Hong Kong, absolutely. Okay, so ready? Here's the idea. The idea is the following. Idea. How to count this? Idea is overcount and then understand how much you overcounted by. The over part of the overcount. All right, so here's how this goes. I'm going to state the entire trick. I'm going to state the conclusion, and then we'll see how to like figure out why this is true. All right, so here's the conclusion. I'll start with the conclusion. The number of elements in the set H times K is equal to the number of the order of H. So the number of elements in H times the number of elements in K. That's a pretty naive guess. You know, you just multiply how many however many h's and however many k's, but there's an overcount. Is that divided by the size of the intersection subgroup? The intersection of two subgroups, again a subgroup. So the intersection subgroup, you divide by that for some reason, the size of that, the product of the two sets, the product of the two sizes. That's exactly how many elements in the group are of the form h times a k. All right, so why? Why is this the case? Why? Okay, so we're going to observe two things. Number one. Suppose I begin with one element. H times a k. I begin with a particular element in the set capital H times k. And then also, plus, I choose an element in this intersection subgroup. Plus, I choose a t. I'm just sticking with what the book decided to use as the symbols. Fine. I choose an element in this subgroup. Then I can produce a new element in H times K. Meaning, I can produce an element that looks new. If you look at H times T inverse times K, all right? If you look at H times T inverse times K, that is the same element as what you started with. However, if you think of elements as an element of H, comma, an element of K, this will appear to be another element in H times another element in K. Namely, this would, if T is a non-trivial element in the intersection, this will look like something other than little h. And the other part will look like something other than little k. So this same element, in conclusion, the same raw element in the group called hk has at least h intersect k number of ways of writing it as a product. That's one conclusion. So conclusion one, every element in hk has at least h intersect k ways of expressing it or factoring it. Yeah. Every element in hk has at least this many ways of factoring it as an h times a k. As an h, an element in capital H times an element in capital K. So all the elements in H times K get named at least H intersect K number of times. So each element in H times K is overcounted at least H intersect K times. When you try to count them just as choose an element in capital H and then choose an element in capital K. That system overcounts by at least H intersect K. So the next thing is to show that it's exactly, we've exactly figured out the overcounting. So in fact, H intersect K exactly accounts for the overcount. And here's the proof of that. Suppose a single element could be expressed in two different ways as an h times a k. Suppose you could write hk as one element in two different ways as an h times a k. All right, then just kind of multiply by inverses on the right way. So this implies that h prime inverse h equals k prime times k inverse. I believe I went ahead and wrote this the right way. Okay? Then these two elements would be the same. Okay? However, stare at this. This here, if you give this the element, if you give this element the name, let's see, what should we call this element? Oh, did I multiply it the right way? I might have multiplied it, just so that it's smoother later. I might have multiplied it the wrong way. Let me multiply it the other way. Let me do it the other way. In other words, I'm going to take the inverse of both sides. So let me backtrack. My argument would have worked just fine the other way too, but I want to write it like this real fast. I want to write h inverse times h prime equals h inverse times h prime equals k times k prime inverse. Okay? Did I do that right? Yes. Okay? So there you go. I'm going to write it like that. So it doesn't matter which way you write it, the argument will proceed the same way, but with an inverse in your argument. All right. So now, notice the both sides of this. Both sides of this are elements in capital H on the left and capital K on the right. In other words, this one element, there's an equal sign between them. This one element, if I gave it a name T, this would be an element in H intersect K. So T, which I'm just defining, this element T would be in the intersection. All right? So we've extracted some element from a hypothetical redundant way of expressing the same element as an H times a K by multiplying and inverses and stuff. We end up pointing at a particular element in H intersect K. And now just watch. Now check. That H times T inverse times K, literally put this T in there, and remember that T is the same as this element. This element is also equal to T. Put T and T inverse in those two spots. This will literally be H prime times K prime. Okay, so what this group theory calculation shows is that every redundancy is explained by insertion of an element in the intersection on the right of H and its inverse on the left of K, which was exactly how our redundancy in step one was defined. Like, if I have an element in the intersection, I can stick it as T and T inverse right there in the middle, and I would get a new representation of the same element. Well, that redundancy is the only redundancy thanks to this part 2. If you had a redundancy, you could express it for some element in the intersection as happening in this insert to the right of H and insert its inverse to the left of K. All right? And so this concludes the overcount. In other words, to count the size, the total number of elements, you first look at all the ways of placing an h next to a k. That's h times k. But each way is overcounted exactly h intersect k times. This is before overcount. And this is the measurement of how much each element was overrepresented. Okay? This will be a magical formula. Because I'm going to explain to you now how it's going to be used. And how it's quite often used in simple group theory arguments. So how is this formula used? It's often used in the following way. It's often used in contradiction style arguments. The way it's used is in some argument, you might be doing some case checks, which my students are familiar with in these group theory type problems. Oh, what if this element has order 3? Then dot dot dot. Okay, in some case checks, you can remove certain possibilities that you didn't know how to remove before, because this side, the left-hand side, in that case that you thought would happen, this left-hand side is bigger than the size of the group. If the left-hand side is bigger than the size of a group, that's a contradiction. Can't possibly be the case. This can't possibly happen. So you use this observation that the size of HK can't exceed the size of the group. You exploit that in arguments. And now that might seem like complete garbage. Like, what does that mean? Well, in the next class on Friday, we'll combine this tool with Lagrange's theorem, and you'll see exactly what it means. You'll see exactly how it's used to deduce this amazing fact, that any group of size 2 times an odd prime is either Z mod 2pz, or it's the dihedral group D sub p. So we'll use this trick in conjunction with Lagrange's theorem, and it'll be great. Okay, so look forward to that on Friday, but I gotta move on to the next segment. And I can't interact with chat because no time. Okay, so, yes, Cayley's theorem, the discussion around Cayley's theorem. Okay, Cayley's theorem is the following. Here's what it states, and then I'll talk about the underlying idea of the proof, and we'll finish the proof on Friday. Okay, so every finite group is isomorphic, so is a carbon copy under some homomorphism, under an isomorphism, to some subgroup of some symmetric group. Right? So what is the point? What is the interest in Cayley's theorem? It's I think I vaguely remember from my childhood that maybe in a couple proofs here or there, Cayley's theorem was used as like a critical tool. Maybe. Okay. But what's the real importance is that if you have a bias towards like groups which like swap things around and do some physical task, like permute things around, you think that that's a real group, and then these abstract other ones are like just made up garbage. Any other abstract group with just a capital G, that's not a real group unless it's physically being a symmetry of a set or something physical happening, moving things around, permuting things, jumbling, scrambling things around. That's what groups really are. Well, that distinction is an illusion. That's the point of Cayley's theorem. All right? And now I'm going to show you the key idea in Cayley's theorem. Cayley's theorem, the underlying proof can be a tongue twister. So the proof is a tongue twister. So the proof is a tongue twister. Tongue twister. Okay. So here's the strategy. Strategy is this. We will first exhibit a homomorphism It's going to be called T. It's going to be called T, okay? T. From G to a symmetric group, an enormous one. In fact, here's the tongue twister. How big is the underlying set that the symmetric group is permuting? The permutation group we're talking about? This huge is actually the size of the group. Okay? It's going to be that big. All right. So we're going to exhibit some homomorphism. And then two, we will show that it is injective. Or we will see. It's going to be quick to see that it is injective. And for this, we're going to use the kernel. The kernel will be trivial for this homomorphism. Therefore, it'll be injective. But then, therefore, it's bijective with its image. The image of a group is a subgroup of the target. Therefore, this homomorphism, if it's injective, it is a bijection onto its image. Not onto Sn, onto its little image in Sn. This thing is an isomorphism. Right? And so there you go. The group is manifested as a subgroup of this S huge. So I have to go and tell you what this homomorphism T from a group to a huge symmetric group is. Where does it come from? And so I'm going to start that discussion. Okay, so I'm going to start this discussion. So let's start this. Suppose I'm going to tell you a general definition. Suppose you have any set whatsoever. It doesn't have to be the numbers from 1 to n. It doesn't have to be that. It can just be any set in the whole universe. Suppose X is any set. Then, the collection of permutations of X denoted perm X is a group under composition, just like it was for Sn for the specific set 1, 2, 3, 4, n. Okay? But you can start with any set and look at all the permutations of that set within itself. This is a group under composition. Let me write out what I mean by a permutation. So a permutation of X is a bijection from X to itself. an injective and surjective map from the set X to itself. Think of it as a scrambling, input-output scrambling of the set X. It needs to be a bijection so that you can undo every scramble. You can take inverses. The identity map from X to X is the identity element in perm X. Okay? And Sn from last week was just the permutations on this set. Okay? But you can take the group of permutations on any set you ever encounter. That's a group. Okay? And so now what we're going to say is in part 1 of this strategy, instead of Sn using the letter n, I will replace it with permutations of a particular finite set. So, in fact, in step 1, we will, in fact, construct a homomorphism called T from G to, very tongue twister, I told you it's a tongue twister, to the permutations of the set G. Now, G is a finite set, so you can go ahead and label if you really need to. You can go ahead and stupidly label every element of G, like put them in a line. So say this is called 1, this one's called 2, this one's called 3. You would end at the integer order of G. And then you can use Sn instead of this perm G. But why? Why not just call it what it is? Perm G. Permutations of this set, G. All scramblings of G within itself. That group is isomorphic to a symmetric group, because if you labeled the elements 1 through n, you would get Sn. All right, so this is the actual kind of object we're going to construct, and here's the name of this homomorphism. The formula is the following. T of an element is, if I have an element in the group, T of that element is the following permutation. The permutation of the group G, which is left multiplication by G. All right? For every element of the group, if you take one, it immediately gives rise to a scrambling of the group. What scrambling? The one obtained by multiply on the left by this element. So the identity will get scrambled to that element, G. G will get scrambled to G squared. H will get scrambled to G times H. K will get scrambled to G times K. This is a scrambling because of left cancellation. So I don't want to say any more about this formula. I want you to think about this, make sense of this formula I wrote on the board. Why is this a legitimate function to begin with? We'll then prove that it's actually a homomorphism and that it's injective. And that'll conclude Cayley's theorem by magic. Okay, so that's the segment on Cayley's theorem for now. We'll complete this discussion on Friday. So now the last thing. The concrete part of the class. I'm going to introduce a new kind of group to you. A new group. Why are new groups exciting? Because you can use them to test for counterexamples. All right. What's the action group? Yeah, but action group is not a phrase that we it's just a permutation on the permutation group of a set. Okay, so new groups, ready? They're called the alternating groups. Now, the alternating groups, one way of defining them will look like, how on earth is that a subgroup? Why is that a group? But it's a very concrete way to get your hands on the alternating group. The other way, it's more apparent that it's a group. So I'm going to start with the other way. Okay, so first thing, what is it? It's called A sub n. Okay, n is an integer from 1, 2, 3, I guess technically 0, 0, 1, 2, 3, 4, etc. Right? And it's a subgroup of Sn. So the first thing you should know is that it's a subgroup of the symmetric group. Okay, great. But apparently according to Cayley's theorem, in some sense every finite group is a subgroup of some symmetric group, or can be manifested, has a carbon copy of itself in some way in some enormous symmetric group. So okay, but an is in Sn, so that's something I guess. Okay, and what collection of permutations is it? So what collection of permutations is it? That's what I'm going to tell you. All right. The one-word answer, the vocabulary word. The one-word answer. The one-word answer is, this an is the set of even permutations. Now, if you first are shown what a permutation is, it's a scrambling of the set 1 through n among itself. It's a bijection from, you can write it in cycle notation, whatever. It's not at all immediately clear that there are apparently two types of permutations. There are even ones and there are odd ones. Okay, and the even ones form a subgroup called an, but I haven't told you what is an even permutation. So I'm going to tell you where one place where the subgroup an was born, one place where it first manifested. It first manifested when people long time ago were doing actual algebra. Okay, actual algebra. So let's take the example of A3. In order to understand where A3 was born, you should write down the following magical polynomial. Write down the following polynomial. Now, how do you write this down systematically? It's the product. You have three variables, x1, x2, and x3. 3 because I'm talking about the third situation. And you write down all the differences between x smaller minus x larger. This is how you write it all fancy like. Okay, notice I don't write x2 minus x1 in the same product because specifically I really don't want to do that, as you'll see soon. All right, you write down this wonderful polynomial. Okay, fantastic polynomial. Just an algebraic, real algebra. We're actually doing algebra. This is abstract algebra. Now it's concrete. Write down that polynomial. And now here's the following exercise you do. Okay, if I give you a permutation now, For example, 1, 2. You all know what this permutation does. I'm using cycle notation. You can apply that permutation to the variables. Apply that swapping to the variables. And this is not something you need to believe. This is obvious. What I'm about to say is obvious. There are either two cases that can happen. Either this polynomial is exactly itself, or it becomes its negative. That's the only two options. It doesn't become some completely unrelated polynomial when you swap the variables according to any permutation. Either the swapping will keep this product, the ultimate product, exactly the same, or it'll swap it by a negative sign. Either this polynomial expression, it's also called the discriminant. This is known as the discriminant. And after class, I'll explain why that is. I'm technically after class. I'll call this the discriminant for now. Either the permutation swaps the discriminant by a minus sign, the discriminant, or it keeps the discriminant exactly the same. All right? And the even permutations are the ones that keep the discriminant the same. So the ones that keep this algebraic expression exactly the same, those are the even permutations. And you know, if you do something and it keeps an object the same, and then you do another one of those things that keeps the object the same, if you do both of them in combination, one after the other, it will keep the object the same. So that's why it's a subgroup. Keeping things fixed forms a subgroup. Okay, more on that later. But negating is if a permutation changes this magical polynomial by a minus sign, it's called odd. So for example, in our running example, let's check out what 1, 2 does. The permutation called 1, 2, what does it do to this polynomial? So for example, what does 1, 2 do to this discriminant? Okay, so we start with this polynomial. Smaller x's minus larger x's. Okay, and then do this permutation. What does this permutation do? This permutation sends 1 to 2, sends 2 to 1, and sends 3 to 3. So just do those to the variables. So x1 goes to x2, keep the minus sign. x2 goes to x1, x2 goes to x1, minus x3 goes to itself, 3 goes to 3. Just apply the scrambling to these variables. x1 goes to x2, x3 goes to itself. All right, so I'm going to erase these. And this is what happened. This is what happened when I tried to swap the variables in that way, according to 1, 2. Okay, but now you look at it. Do some algebra. Is this the same as the original discriminant polynomial, or is it off by a minus sign? Well, you notice this part became negative. That became a negative of the other. And then nothing changed on the other part. No more negatives happened. This part became here, this factor went over here, and this factor went over here. So the total algebraic expression became negative. And so 1, 2, this simple transposition 1, 2 is an odd permutation. 1, 2 is odd. Okay, one more example. This will just be in the video so you can watch it later. You can go to wherever it is you go after this class. So I'm just going to keep going with this concrete stuff so you have it for reference. Let's do another example. Let's ask, is 1, 2, 3 even or odd? Is it in A3 or is it not in A3? Okay, let's check. What happens to the discriminant polynomial? Okay, 3 because we have 3. We're in S3. So the 3 is explaining why I'm looking at 3 variables and permuting them. Okay. So I apply this permutation, apply it to the variables. Okay, so in this permutation, 1 goes to 2. So 1 goes to 2. And x2 becomes x3. And x3 becomes x1. It cycles back, right? It's cycle notation. Okay. x1 becomes x2. Minus x3 becomes x1. x2 becomes x3. x3 becomes x1. And now you have to look at this new factored polynomial and ask, was it the same as the discriminant or was it different? Okay, well, look carefully. X2 minus x3 and x2 minus x3, same sign. So no sign change yet. Okay. x1 minus x3. Ooh. Minus sign. Minus sign emerged. But then, at the same time, I get a second minus sign. Minus sign. Two negatives make a positive. And so this product stayed put. It didn't swap to its negative sign, to the negative polynomial. All right? Stays put. Stays the same. Discriminant stays the same. So this was even permutation. Okay, so now I'll let you figure out exactly what the subgroup of S3 called A3 is, and then we'll talk more about it on Friday, and there will be office hours on Friday, but I'll talk to you about that on Discord, so we can do way more examples and be more relaxed about the pace and stuff. That'll be on Friday. Okay. Okay, so let's go check out now what the hell happened in this chat or on Discord. Check Discord first because it's my students. Okay, they're asleep. All right. Okay. Yes. The videos will get uploaded to YouTube anyway, so don't worry about that. Would I throw in the word group action here? The phrase group action happens next week in one of the thirds of this 45-minute lecture craziness. Yes, group actions happen eventually. Okay. Yes, Kappa Klaus is real. Surprised Pikachu face. Two permutation whose signature were both negative get a positive signature when composed. But the puzzle, the thing that you have to learn how to explain to someone, is what the hell is signature? Not at all obvious that permutations have a signature to begin with. I challenge you to explain to someone who's never seen, who's just learning what a permutation is, that there is even a notion of signature. That's the content of the discussion, not then that two negatives form a positive. That's clear from arithmetic. Even though that is not clear. Have you ever tried explaining to a child why two negatives multiply to a positive? Not easy. Yeah. No. The cycles, all we know is how to express permutations as cycles. But then, so what? How do you extract that some of these are even and some of them are odd? Not at all clear. It emerges from trying to use symmetry in algebraic manipulation, like this discriminant thing. Oh, one last thing. Why is the discriminant called the discriminant? I should probably end with that so that people understand where this word comes from. Why the word discriminant? Why is this crazy product called the discriminant? Okay, so here's what it comes from. Like, in school, you learn how to solve algebra problem, like quadratic equation, right? And suppose we knew the two roots. Suppose suppose root 1 and root 2 were two roots. Then you learn something like this. It's like, then R1 times R2 is B. And then the sum of them is negative A or something. Right? And how do you know this? It's like, you know that the polynomial factors, and you collect the terms and you'll get that R1 times R2 has to be the number B, and R1 plus R2 has to be the number negative A. So you know that. But here's the thing. Let's write down the discriminant. And hopefully this works. Let's write down the discriminant R1 minus, where X1 and X2 are now their two roots, R1 and R2. So, no. Let's square the discriminant. Square the discriminant. I messed up. Let's square the discriminant. Let's just square the discriminant. So in this case, the discriminant is just the difference between R1 minus R2. And just because I want the explanation to work, I'm going to square it. Purely because I just want this explanation to work. To tie this discriminant with the previous one. The previous one didn't have this square, and it's very important that we don't use the square. But this one, in here, I'm going to square this difference. And what do you get? You get the following thing. R1 squared minus 2R1 R2 plus R2 squared. I believe I did this right. Some kind of FOIL or something. Okay, but now I'm going to do a little bit of algebra to this. This is R1 plus R2 all squared. Okay, this is R1 plus R2 all squared minus 4 R1 R2. Why did I do this? Because if I now write this in terms of A and B, R1 plus R2 is negative A, and I'm squaring that, minus 4 times R1, R2, which is B, which is A squared minus 4B. All right? And this, where I chose the most terrible letters for the coefficients, this is exactly the thing that happens in the quadratic formula. This is what is in the square root in the quadratic formula. So if I put the square root back in, you'll see the little piece of the quadratic formula come out, and that is exactly this expression, R1 minus R2. And the connection between that discriminant and we sort of generalize that to arbitrary numbers of variables by multiplying all products of differences, but only represent a difference one time. Don't put x1 minus x2 and x2 minus x1 in the same expression. It's kind of like taking the square root of b squared minus 4ac, or in this case, a squared minus 4b. So that's the connection. That's why we use the same word, discriminant, when talking about this algebraic expression in any number of variables. That's the link with high school algebra. Okay. Why is it fair to consider trinomials in R or C rather than any ring? Why is it fair to consider? I don't know what that's asking. One, two, three is a permutation. Right. 1, 2, 3 is a permutation. It's a permutation. The NICO, it's a permutation written in what's called cycle notation. And what this permutation does, NICO, is the way you read it is the symbol, the element 1 gets permuted, gets sent, musical chairs, gets sent to 2, and 2 becomes 3, and 3 cycles back and becomes 1. That's just how you read this cycle in cycle notation. But you should go read about cycle notations, so cycle notation and how it's used to encode scramblings of a set. Yeah, it's confusing. It's not a vector. It's how to scramble these variables. It's instructions for scrambling the x1, x2, x3 variables. Okay. Super permutations? That sounds fancier than a permutation. Your x squared plus ax plus c is posed in R or C. I don't think I ever said that. I mean, the original context was in R and C, but the symbolic manipulation happens much more generally. So there is no. Does a vector have a property of even or odd? No. A vector is technically an element of a vector space, and the amazing thing about a vector space is that no one vector, other than the zero vector, no one vector is any different, so to speak, from any other vector. No one vector has any distinguished property that's special to it that isn't shared by any other vector in the absence of any further structure that you secretly imposed on the vector space. You might say, oh, no, some vectors are unit length and others aren't. Yeah, well, you just made up a new rule. No, there is no such thing as unit length if all you start with is a vector space, an abstract vector space. So in an abstract vector space, there is no notion of this vector or even that vector. There's only the distinction between a zero vector, that vector is distinguished, and then a non-zero vector. So yeah, there can't possibly be a notion in original vector space linear algebra that says some vectors are even and some are odd, because all vectors that are non-zero can be rotated, can be there's a linear transformation of the vector space which sends one non-zero vector to any other non-zero vector. So they can't possibly be distinguished. Yeah. There are no special vectors in a vector space other than the zero vector. You might say, what about the unit basis vector? Yeah, well, you went ahead and chose a basis. So of course, once you choose a vector, that vector becomes special. But why did you choose that vector and not some other basis? Anyway, so no, there is no such definition of even and oddness of abstract vectors. Once you add in some extra structure to the vector space, like, I don't know, there's all kinds of conceivable mathematical structures you can impose on objects, then maybe sometimes you'll get a notion of an even or an odd vector. But I've never seen that. Actually, in some sense there are, yeah, in some sense there are situations, very special situations, where there are instances of even and odd vectors. That is true. But it's not just a vector space. It has all this other structure. Like you might have seen, given your comment about super permutations, well, there's also super representation theory, or super Lie algebras. And there, a vector space is divided into like the 0th graded piece, like the even part and the odd part. But that's not a random vector space. That's a very delicate situation. Oh my god, Young's Lab is here. Oh my god, Young's Lab. Okay, Dr. Young's Lab is an educator of some sort and does chemistry or something. And they have this course actually every Thursday on the science of color. That's the only interesting thing that he ever talks about. So you should all check that out. You should all follow him only for that reason, not for any other reason. The science of color course, mind-blowing, very interdisciplinary. How was my break? My break was boring. What is this? What is this link? I think I know what that is, and I think I've seen that. That's embarrassing. I don't like that my reputation is being used is being sullied. Like, what is that? What am I, some sort of joke? Yeah, I know that. I know that, Dr. Young's Lab. It was embarrassing when I saw that. I immediately just shut down the internet, and yeah, it was terrible. I remind you of Healthy Gamer GG. Gee, I wonder why. I wonder what it is about me, Naiko, that reminds you of Dr. K. I wonder. I wonder what it is. Gee, I wonder. Probably the hair. Yes, Dr. Young's left. That's right. Dr. Young's left. That's funny. Okay, but yeah, folks, you know the drill. I have to go, like, learn some Calc 2 or something. Fractions. I have to learn how to add fractions or unadd fractions. And so that happens in an hour, so I have to cram for that. Now I gotta get you out of here. I gotta dump all 11 of you to, let's see, where are you guys going? You guys want to go? Who's out there? Is Gath out there? Gath is out there, but I doubt. Yeah, okay, she's not. Out there. Oh, wait. Professor Peter's out there. Okay, go talk to Professor Peter. Go tell him about discriminants. Go tell him about even and odd permutations. He'll already know everything you say, but he's a nice guy, so he will humor you, and he will nod and smile. So go. Okay. He also rejected. Oh no, did he? Hold on. No. He accepted. All right, ready? Go teach Professor Peter everything that he already knows, and he will humor you.
Some calculus stuff this semester. I think Calc 2, right? So go ahead, pop over there, ask him all your questions so that you don't ask me any of those things. Oh no, Tyrion. No, don't show him. Welcome. What's the topic? Right now, I'm working on a little homework problem for a student that had emailed in a question. They said they weren't going to be able to make the stream. And it is volumes of surfaces of revolution. I know your Calc 2 classes, BMP, I think you flipped the order of the stuff that we do, or that I do. You guys do integration methods first, I think, and we do integration methods after applications of integrals, but yeah. All right, so right now what we're doing is a little bit of washer goodness. We've got this integral here that I'll go ahead and set up. Let me just copy paste that because I'm not going to remember this. Yeah, you've done this already? Are you guys in that abstract algebra class? How's that going? Oh, you guys tackle that in Calc 1. Gotcha. Makes sense. All right, so let's see this. Pi times the integral from 0 to 1 of 9. Oh, no, I already wrote all this stuff out. I copied and pasted the wrong thing.